Any questions, comments, concerns that aren't related to vaccines? All right, so I put on the board there chapter 3 and 6 together. So chapter 3 is acid-base chemistry. Chapter 6 is sort of a broad discussion of chemical reactions. So really the rest of the semester, we're going to be looking at chemical reactions. And all of Orgo 2 is chemical reactions. We're going to start with the acid-base reactions, which are really pretty much, hey, if you can understand the proton transfer reaction, you're going to be more or less fine for all the other reactions we do and for biochemistry. Like this is, acid-base chemistry is sort of fundamental to reactions. If you don't get acid-base chemistry, you're going to really struggle down the road. Okay, so what happens when an acid reacts with a base? Anyone? Yeah. Both are true, actually. Yeah, that's a deeper answer than that's a good answer. That's what happens when you base your entire lecture on, like, I think the students are going to tell me one thing. So the acid donates a proton if the acid-base reaction is what we call a Bronsted-Lowry acid-base reaction. The base is going to donate electrons under any definition. All right, so there's the Bronsted definition of acids and bases, and there's the Lewis definition of acids and bases. Lewis is the broader definition, and Lewis basically explains, I don't know, 90% of ionic reactions. And we're going to get out of this a conjugate base and a conjugate acid. And this is going to be an equilibrium process, okay? So you've got this, in a Bronsted reaction, you're going to have a proton sort of bouncing back and forth between two atoms. Let me go ahead and write up the All right, so like I said, in the Bronsted theory, an acid is a proton donor, and a base is a proton acceptor. In the Lewis theory, which is more general, the base is an electron. A Lewis base is an electron donor. A Lewis acid is an electron acceptor. And here's the thing about chemical reactions. All right, this is chemistry. This isn't physics, so we're never changing the nucleus. All right, if I dump into a flask a bunch of carbon and hydrogen and oxygen, I'm going to have carbon and hydrogen and oxygen at the end of it. All right, we're not changing elements. We're only changing bonds. We're breaking bonds. We're making bonds. We're moving electrons around, in other words, right? A bond is a pair of electrons shared between atoms. So all we're doing in a chemical reaction is affecting the electrons. And therefore, the way to think about chemical reactions is to think about the electrons. So that's why the Lewis theory, Lewis acid-base theory, really is a lot more effective. It's harder to get, maybe just a little bit. So we're going to start with proton transfers. The nice thing about that is you've seen proton transfers before, and again, if you're interested in medicine or biochemistry or anything that happens in water, proton transfer reactions are really the sort of the core of chemical reactions. Why? Proton transfers happen all the time in water. We think about H2O, and we think about like this H is always bonded to this O and to this other H forever and ever. That isn't what happens. I usually sometimes bring a water for this. Right, you got a bottle of water over there. There are protons hopping on and off oxygens, you know, in that amount, trillions of times a second. All right, so protons are bonded to an oxygen. Some other oxygen will come and take that proton off. The oxygen that's left behind has to grab an H from somewhere. This goes on really fast all the time. Okay, so let's, like I said, let's start with a simple one. Draw the product of that reaction. And identify which is the base and which is the acid. I wanted to buy myself some space. All right, another 15 seconds or so to get that. All right, so the product, first of all, you have to identify what the base and what the acid is. And I hope I made that easy here. Hydroxide is a base, probably the first base you guys were told about. And the reason I asked that initial question, a lot of times when I ask, in a freshman level course, what happens when an acid reacts with a base, I get some generic answer like, you get water. Right? In this particular case, you do. If hydroxide is the base, you're going to form water. Water is the conjugate base of hydroxide. But there are a lot more bases than hydroxide. If hydroxide's not the base, you will not get water, unless H3O plus is the acid. Okay, so here we're going to move. If hydroxide is the base, and this is an acid-base reaction, HCl's got to be the acid. Again, you should probably, I think it's almost 100% that you guys know hydroxide's a base. Maybe 98% that you know HCl is an acid. So HCl is a strong acid, hydroxide's a base. So the proton, if we go by Bronsted definition up there, HCl is an acid because this proton is donated. Hydroxide is the base because the hydroxide is accepting the proton. So the product would be water and chloride minus. All right, so this is going to be a base, an acid. All right, so the protonated base is the conjugate acid. The deprotonated acid is the conjugate base. Questions? All right, so on the one hand, I really, really want you guys to be able to identify conjugate acids and bases. All right, again, one more time. The conjugate acid is simply the base that's been protonated. The conjugate base is the acid that's been deprotonated. But the use of the word conjugate really betrays a bias. All right? Water doesn't know it's a conjugate base, or sorry, a conjugate acid. Water's water, right? It is the conjugate acid of hydroxide, but it's also the conjugate base of H3O+. Water is an acid and a base. There are quite a few molecules that can do that. But where I'm going with that is a conjugate acid is just an acid. A conjugate base is just a base. All right, there's nothing special that adds the word conjugate except we draw it on the right as products. It would be just as fair to write this reaction as chloride minus plus water gives you hydroxide and HCl. Questions about that? All right, so hopefully you're up on that. Also, I've got this equilibrium arrow, right? So it's a back and forth. Which side is favored, do you think, here? Got to vote for a right. All right, so I wanted to put this over at the side. Things you need to think about in any acid-base reaction. All right. Which proton is acidic? Right now, it's not actually simple. If you just look at this, you've got the H on HCl, you've got the H on hydroxide. Any proton could be the acidic H. When we start looking at bigger molecules, more complicated molecules, there's going to be a lot of H's. You're going to need to be able to identify which proton is the most acidic. Which atom is the electron donor? The little star there means it doesn't have to be an atom. It could also be a bond. We'll see that down the road here pretty quick. Right. By this question, I mean which atom is basic. All right, so this one's a little easier. You got protons in both molecules. You have electrons in both molecules too. Let me draw those in. So we got 3 lone pairs on oxygen. We got 3 lone pairs on chlorine. We have 2 bonding pairs, one between the O and the H, one between the H and the Cl. But we also have a negative formal charge. All right, that negative formal charge on oxygen means, it's negative. It's got an abundance of electrons. I always ask this. I like to use analogies of electrons being money and the atoms being like people with money. So when I ask this question, I'm not asking about personalities. I'm just like, if you go out to dinner, and you're just average Joes, and everybody's got a 20 in their pocket except for one guy who's a billionaire, has billions. Like, who's going to pick up the tab? Now, I appreciate people are weird, and so the billionaire may not pick up the tab, but the billionaire is more capable of picking up the tab than anybody else. So that's what I'm talking about when I make these analogies. That hydroxide, the oxygen has a formal negative charge. It means it's got an excess of electrons. Of all the atoms pictured there, that oxygen can give away electrons the easiest. That's not always going to be true, but it's often the way to bet. And so that's going to make the negative oxygen be basic. And I want you guys to hang on to hydroxide. You guys know hydroxide is a base. In organic chemistry, we're going to see a lot of negative O's that are basic. So like if that wasn't OH minus, if it was O methyl minus, that's a strong base. If it was O ethyl minus, that's a strong base, right? So the more something looks like hydroxide, the more basic it's likely to be. And then the third question, which side is more stable? And by that, I mean which side is favored, what I just asked you there. And then kind of parenthetical to the parenthetical, by how much are the two sides favored? Or is the one side favored? All right, so here, which H is most acidic, which atom's most basic, those are the easier two questions. Which side is favored and by how much is the bigger question. All right, and so here we have a negative formal charge on both sides. We have hydroxide, we have HCl. The side that's favored is going to be the side with the weakest acid and the weakest base. It's kind of this is how it will always work out. The side with the weakest acid will also be the side with the weakest base. The side with the weakest base will be the one with the weakest acid. So what you want to compare is the base and its conjugate acid, or the acid and its conjugate base. That's wrong. Delete, rewind, whatever. I always draw that pair wrong. You want to compare the two bases or the two acids. Yeah, so delete everything. I'll stop. I'll pause for a minute. I always do that one wrong. All right, so you can't really compare hydroxide and water, right? Which one's more stable, hydroxide or water? Water. Water's more stable. You don't learn anything by that, right? Water is the conjugate acid of hydroxide. Hydroxide's the conjugate base of water. You don't learn anything. What you need to compare are the two acids. So the acid on the left and the acid on the right. Usually you're going to call that acid and conjugate acid. Which one of those is more stable? If it's obvious which one's more stable, the more stable one's favored. Or you can compare the base and the conjugate base. Again, if you can figure out which one of those is more stable, that's the way to go. So for comparing the base, we're going to use a method called ARIO. You're first going to look at the atom, then you're going to look at resonance, then you're going to look at induction, and then you're going to look at the orbital. In that order. Looking at the atom means the more electronegative atom is going to prefer to have the electrons, right? So a base is an electron donor. It's giving away electrons. So you're going to have this lone pair of electrons or a bonding pair of electrons on the base or a negative charge. So we have a negative O versus a negative Cl. The more electronegative atom generally will prefer to have the excess electrons. The more R is for resonance, the more delocalized that charge is, right? If we can delocalize the charge. So there was actually an example of this in one of those stability questions on exam 1, right? A delocalized negative O is better than a localized negative O. By delocalized, I mean resonance. You can draw a resonance structure for that negative charge. The other thing to keep in mind with ARIO is this is a general guide. It is not like gravity, all right? You're going to see some exceptions to ARIO. Comparing the acids will usually come down to pKa. We'll talk about that in a second. Okay, so I need to get this out of the way. Because I have trouble talking about these reactions without doing this. Hard to see that on my phone. Okay, so when you do these reactions, like I said, a chemical reaction involves breaking a bond or forming a bond, usually both. The bonds, all bonds are electrons, shared electrons. So if you follow the electrons, you can pretty much keep track of what's happening in the reaction. And the way we do this is with curved arrows. So I'm going to redraw this. And you'll find this discussion of curved arrows in chapter 6. So a curved arrow represents the motion or behavior of electrons, not atoms. Some of you, I mean, I don't want to cast aspersions. Some of you probably had outstanding high school chemistry teachers. Some of you probably had poor ones. Some of you had, most of you had middling ones. It's the way the world works. Occasionally, I will have students who want these curved arrows to represent the motion and behavior of atoms. Perfectly logical thing to want. I'm going to show this H going, all right, we have an H going from a chlorine to an oxygen. An arrow would be a good way of showing that. This H goes over here. But if it turns out, if you do that, if you use the curved arrows for atoms, you will get yourself in trouble. If you use them for electrons and electrons only, it will work out. All right, so how about I stop philosophizing and show you what I mean. So we would represent this reaction, this proton transfer, with two arrows. One is going to be from the oxygen to the H. All right, remember the charges on this H, partial positive on the H, partial negative on the chlorine, full negative on the oxygen. That curved arrow is going to go, the arrow is always going to start with electrons. So a lone pair or a bond or a negative charge. Electrons start the sequence. This curved arrow, this blue curved arrow right there that I just drew, formally what that means is a bond has formed between the oxygen and the hydrogen. Okay? Right. Hydrogen cannot have two bonds. So you're not done. You will see some reactions where there's one curved arrow, right? If I have like an atom that can have one more bond, say I have a carbon that's got 3 bonds and a positive charge, and then I have something else that's got electrons. It could just make a bond to that carbon. That'd be fine. Nothing else has to happen. Here, something else has to happen. And what has to happen is this H has to lose a bond. And so the way we represent that is another arrow starts with the bonding electrons in this bond and goes to the chlorine. And by drawing those two together, we're saying the OH bond forms at exactly the same time as the HCl bond breaks. All right, so this oxygen, one of the lone pairs in this oxygen has gone to make a bond, so the oxygen's going to have only 2 lone pairs now, and a lone pair has turned into a bonding pair. Right? This blue arrow here turns into a bonding pair. The bonding pair between HCl, right? The chlorine has 3 lone pairs at the start. A bonding pair becomes a lone pair on the chlorine. The chlorine winds up with 4 lone pairs and therefore a negative charge. All right, so in ionic reactions, the curved arrows are like a circuit. They're going to go head to tail, head to tail. You're never going to have arrows come together. Right? Arrows are never going to come together like that. They're never going to go away from each other. Like that. It's going to be a circuit. Bang, 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 bang. All right. So, yeah. So in this reaction, curved arrows, bang and bang. The back reaction could also have curved arrows. Again, the arrows are going to start with the negative charge, the electrons to the H, break that bond. That would be the curved arrows going back. Now, I think everybody said the right side is favored. All right? And one way to think about that here, if you think about hydroxide and HCl, right? HCl is a strong acid. Hydroxide is a strong base. Although for reasons we'll get into, that's a hard thing to say. Weak and strong is always a relative term. Right? If I say I'm strong, maybe you believe it, maybe you don't. If I say I'm strong and you believe it, you're comparing me to somebody you know. Right? Like you've got some idea of what an average person is like. If you don't believe it, you're also comparing me. And you're like, I had a friend in school that could bench 500. You probably can't do that. You'd be right. Strong and weak's always a relative term. Okay? But when we say hydroxide is a strong base and HCl is a strong acid, we mean that in water. Right? So in water, hydroxide is a really strong base. HCl is a really strong acid. And, so let me ask this question about water. Is water a strong acid or base? It's not. How do you know that? There you go. Right? If you can pour it down your throat, it is not a strong acid or base. Like, well, if you can pour it down your throat and survive and enjoy the experience. Okay, so water is not a strong, water is a weak acid and base. Here it's an acid, right? So this is going to be a weak acid. And you may not know about chloride ion. Water you have a lot more experience. You actually have a lot of experience with chloride. Can you eat chloride? Yeah, as I say, everybody's shaking their head. I'm like, you can look at my blood pressure and tell that I'm not supposed to eat chloride, but not because it's a strong acid or base. All right. You guys eat, you're Americans living in America, you eat a lot of salt. Sodium chloride, just throw it down the gullet. Again, it stings a little bit. You get it in a hangnail. You can taste it, but that's not an acid-base reaction. Chloride's also a weak base. So here, we got a strong base reacting with a strong acid to give a weak base and a weak acid. This means that this reaction is going to very much favor the weak acid and base. All right. The weaker acid and base will always be favored, and they're always going to be on the right. So one last thing here, and I'll get into this a little bit on the next reaction I show you. pKa is another way of thinking about an acid-base reaction. Again, pKa formally only applies in water and to acids and bases that can function in water. We use it more generally in organic chemistry. Like I said, I will need to get into that in more detail. But you can compare the pKa's of the acids in the reaction. The higher pKa will be favored. And so in this case, the pKa of HCl is about -7. And the pKa of water is about, well, it's technically 15.7. I always remember 14. All right, so water's got a higher pKa, so it's favored. All right, everybody having fun so far? I think I'm going to swing I got all the boards covered today, so I'm going to come all the way down here. So like I said, you guys should be able to use hydroxide as a base coming out of Gen Chem, either 111 or high school or whatever. Hydroxide is a really common base, sodium hydroxide, and it doesn't so much matter. thermodynamics of the acid-base reaction don't matter so much if it's lithium hydroxide or potassium or sodium or cesium or ammonium. What matters is just the hydroxide. There's some kinetic concerns that that ion gets into, but you'll notice here I haven't paired the hydroxide with anything. You can't have a bottle of hydroxide. Right? I've got a lot of hydroxide up in my lab, but it's all lithium, sodium, potassium, something else. Right? There's no just a bottle of negative ions. So I want you to do the same thing you did over there. Identify the acid, the base, give me the products, try a mechanism. So we would call these curved arrows here, we would call that the mechanism of the reaction. All right, give that a shot for this reaction. I'm going to go back to early days and I'll draw in all the electrons. Nomenclature and functional groups are your friends. All right, so I see a lot of people have stopped writing. I know some of you are still going. Before I put up the answers, what's the functional group here? That's an amine. What's the functional group here? Carboxylic acid. That's a hint. All right, so I will tell you, I always make this joke, and then if you have me in Orgo 2, which I don't think you will, I don't think I'm teaching Orgo 2 next semester. But if you do, that carboxylic acid can be a base. All right, a base is an electron donor. You got two oxygens with electrons on them. So if you treat acetic acid with a really strong acid, it can turn around and be the base. But the fact that the word acid is in its name means that it's usually going to be an acid. All right, another 60 seconds if you need to switch those around. Okay, so I've drawn the products. Carboxylic acid is going to be a proton donor, and even though it's got two different kinds of protons, right? So if you took an NMR of acetic acid, you'd have this broad signal down out on the left, downfield, that integrates for 1. You'd have a sharp singlet along about 2, 2.5 somewhere that integrates for 3. And any of those protons could be the acidic proton, right? A proton is a proton. The proton on the nitrogen could, in fact, be acidic. And again, in a lot of these cases, it comes down to if you want to figure out if a molecule can react as an acid, it depends what the base is. If you want to know if a molecule can react as a base, you want to know what the acid is. This NH, that H can be acidic under the right conditions. Right? If I treat that with the right base could pull that proton off the nitrogen. What you're looking for here is, of the 3 hydrogens, there's the one on nitrogen, there's one on oxygen, and there's one on carbon. You want to kind of come back over to this ARIO. Again, the atom, resonance, induction, and orbital. Don't worry about induction and orbital today. Atom and resonance. What's the most electronegative atom in that pair? Oxygen. So if something's going to accept electrons, all right, go to the Lewis definition. If there's an atom that's going to accept electrons, it's probably going to be oxygen. So if I'm going to put a negative charge somewhere, I'm going to put it on oxygen before nitrogen or carbon. All right? CHs are only acidic under a few circumstances. Those circumstances are really cool. We have a lot of fun with them in Orgo 2, but you won't really see a lot of acidic carbons, CHs, in Orgo 1. The other thing is, if I put a negative charge on this oxygen, it's delocalized. So we get both A and R, in this case, leading that OH proton to being the acidic proton. All right, so that makes the nitrogen is really the only thing with, I guess there are CHs here too, I didn't draw. So in terms of electrons, we have a lone pair on nitrogen, we have lone pairs on oxygen. Again, which one's more electronegative? Oxygen. So nitrogen, being less electronegative, is more likely to give electrons away than oxygen is. Right? So our curved arrows wind up doing this. Start with the electrons on the nitrogen, draw a bond to the H, the partial positive H, that makes our NH bond, and then the OH electrons become a lone pair on the oxygen. Let me draw in these lone pairs, and I can show you what I mean by resonance. All right, so this is a carboxylate. It's fine to draw it this way. This kind of goes back to chapter 2 stuff. You can draw either resonance structure, right? If you have a molecule that's got multiple significant resonance forms, you can draw any of them. Here, they're actually equal. So if we go from the carboxylate, we can take one of these lone pairs, make a pi bond. That breaks the pi bond, kicks those pi electrons up onto the other oxygen to give a lone pair. And what we have then is that. And it looks like I just flipped it over, but actually those electrons are delocalized. By delocalized, I mean there's a lone pair here that's neither only on this oxygen or that oxygen. They're kind of spread over those 3 atoms, the O, the C, and the O. And that stabilizes it. The more you can spread charge out, the more stable it is. So in this acid-base reaction, we put the negative charge, the excess electrons on the more electronegative atom, and we delocalize them. All right, so we get acetate ion, and this is an ammonium. So this is dimethylammonium. This would be dimethylammonium acetate. All right, so acetate is the conjugate base. Dimethylammonium is the conjugate acid. Now, which side is favored? Take 30 seconds and consider which side you think is favored. This would be where a zoom pole would work nicely. All right, who thinks the left is favored? Who thinks the right is favored? Anybody abstaining? That was a lot of, why do you guys think the right is favored? Did you read the textbook?
Because the conjugate base has like a more negative end, so it's
Yeah. So you're looking at really the stability of the lone pair. Like what this comes down to, what acid-base reactions come down to is how stable is the extra electrons. There's a lone pair or a bonding pair, but for now let's stick with a lone pair. There's a lone pair that's got to be somewhere. All right? On the left, that lone pair is localized on the nitrogen. On the right, it is delocalized on oxygen. All right, so I'll tell you, so working with pKa, and we're going to talk about pKa next, right? So if you use the pKa, like if you know the pKas, or even better for you, if I give you the pKas, that is like, don't argue with it. Don't think about it. The higher number is the weaker acid, and it's favored. Don't ask yourself why. Well, that's just because pKa is a direct measure. That's what we're measuring. We're measuring how stable is this acid. So the higher number means it's more stable. If you have to use structural arguments, and you guys did this really well, right? If you have to sort of look and see, do I think the structure of this base is more stable than that base, or do I think the structure of this acid is more stable than that acid? That often gets hard to tell. Right? I mean, you guys, at this point, just starting out, you're going to hate that. I still miss these occasionally, right? And as they get close, I'm not going to expect you guys to, pKa of this one's 4.8 and this one's 4.72, like you can tell those apart. All right, I'm looking for big gaps. Again, we'll talk about pKa in just a second. Okay, so exactly right. I'm going to explain this again. This reaction favors the right, even though there are charges. So again, you guys you're doing a really good job of sort of subverting my expectations today. Right? A lot of people will come in and say, oh, the left must be favored because everything's neutral. And that is, a perfectly fine way to guess. And often is right. Okay? So a lot of times, a reaction that has the formally neutral pair is more stable. I put this reaction up for a reason. Actually, John, what's your question first?
do you want us to draw a resonance?
No, that's what I mean. Like, you don't, I drew the resonance to explain it. All right? So you guys don't have to, if there's an acetate, you could draw it if you wanted, right? You could just draw this as, I mean, honestly, I don't expect that, but that's what acetate is. The two CO bonds have the same bond length. The oxygens have the same charge. If you get a crystal structure of an acetate or a carboxylate, that's what it looks like. I almost always draw the double bonded O and a single bonded O minus. And I almost always have the double bonded O going up and the O minus to the right, but you could draw the other one too. Like I said, resonance structures, they're just different. Resonance structures, again, a reminder back to chapter 2. Resonance structures are different ways of drawing the same molecule. All those Lewis structures are valid. Right? Equilibrium means something has changed. Conformation has changed. A bond has changed. There's been some chemical or dynamic process where the molecules actually change what they are. Resonance structures, they haven't changed any between the two. So the reason I bring this one up, and like, I don't know, in a lot of ways, This is like the reaction. Okay, I don't know where you guys are all going. Some of you, I hope, will do chemical research someday for a living. Some of you may never take another science class. From that person who never takes another science class all the way to like someone who gets a PhD in chemistry, this is a reaction you should know. Nature, biological creatures on Earth, carboxylic acids tend to be the strongest acids you're going to see. There's a few exceptions in biochemistry, but not many. By the same token, amines tend to be the strongest bases you see, and they combine in the phrase amino acids, right? Make up the protein, all the many of the molecules that make us move around, talk, think, worry about tests, that sort of thing, are amino acids. So how these two functional groups interact with each other is critical. And even if you don't really get it today, if you're kind of like, I don't like that the ions are favored over the neutrals, I want you to know this. Like if you take nothing else away from this class, take that. If you put a carboxylic acid with an amine, the conjugate acid and base are going to be favored. The carboxylate and the ammonium salt. All right, so let's do pKa's. Let's break this. So we sort of did a structural argument up above. So if I'm right here, the pKa's, right, the pKa of the acid on the right needs to be a bigger number than the pKa of the acid on the left. And it turns out that's true. So pKa for acetic acid is 4.5. Dimethyl ammonium is 10.4. Now the next question I usually get, I'm not going to ask you because nobody so far is answering questions the way I want. You're getting the questions right, so you're putting one over on me. Do you have to memorize pKa's? Yeah, kind of. I can't tell if the people shaking their head were honestly telling me they don't think they should. Did you honestly think you shouldn't, or you just don't want to?
A little bit.
Cool. So I don't want you necessarily to memorize that the pKa of dimethyl ammonium is 10.4, or acetic acid is 4.5. What I want you to do, again, is sort of like the chemical shifts. Do it sort of in ballparks. Carboxylic acids tend to be 3 to 5. Protonated amines tend to be like 9 to 11. So that's what I mean. That, just kind of put them in an area. You don't need to know that it's 10.4 and 4.5 if you know 9 to 11 and 3 to 5. There's no overlap there. You know that the ammonium salt's going to be favored. Okay. The other thing, you can estimate the equilibrium here. Right? This is K equilibrium is going to be, so this is going to be there's a whole lot of stuff here that I am really skipping over, okay? It's in the text. It's in the PowerPoint shows. And you should know it. So from this class, most of you are going to go on to 223 or go 2. The fourth chemistry class, so if you're pre-health, if you're pre-med, I guess, you would have to take Chem 280, Gen Chem 2. You will get a treatment of this. So those of you that came in early and there were lots of equations up on Professor Ding's screen, that's Gen Chem 2. All right, you will do mathematical treatments of this out the wazoo. And it's important you be able to do that, all right? I'm not belittling that. Organic chemists tend to ballpark this. So pKa comes out of acid dissociation constants in water. All right, so acid plus water. Water's a weak base. Water can take that proton. We'll do one of those here in a second. But it's, where did I put it? I put it over here somewhere. This is an important thing to remember. pK units are log units. All right, so if one acid has a pK of 5 and another acid has a pK of 6, the one with a pK of 5 is 10 times stronger than the pK of 6. And so then you can use this. I guess the other thing is this all falls out of the Henderson-Hasselbalch equation. I'm not going to derive that. That's in the book. You'll look at it a lot in Chem 280. I'm going to ask you guys to sort of use pKa numbers. You can memorize how to do that. Ultimately, if you go through Chem 280, you'll have to learn what it all means and derive it. So it's worth looking at now. So the equilibrium constant's always the concentration of the products divided by the concentration of the reagents. And here is the cool thing. I just skipped like a whole bunch of algebra there. It's always going to be the equilibrium constant for an acid-base reaction is going to be 10 raised to a power of the pKa of the favored acid minus the pKa of the unfavored acid. I should have just lied to you and said one of these was 0.5. So I'm going to show you organic chemistry math now. Okay, I've already taken a bunch of shortcuts. 10.4 minus 4.5 is 5.9, right? Maybe? Okay, good. I'm going to say it's 6. Right, we're not going to deal with anything. So this is along about 10 to the 6th. 10 to the 6th is a million. Okay, so if I mix acetic acid and dimethylamine, the right is favored by a millionfold over the left. And that might seem like a lot. It is quite a bit. But keep in mind, if I have like 10 milligrams of each of these, I've got something on the order of like 10 to the 20th molecules. All right, 10 to the 20th is a way bigger number than 10 to the 6th. So in solution there, you can have, like, there's enough of these two to do some chemistry. And that's why in biochemistry, these are the acids and the bases, right? It's mostly the proton has mostly transferred to the carboxylic acid, but you can find in solution a protonated carboxylic acid and a deprotonated amine, and they can do chemistry. All right, so this is an important thing to fall out of that. And then the other is, well, I tell you what, let's do another reaction real fast. And I shouldn't have put these. So same thing there. Identify the acid and base. Draw a mechanism. Draw the products. Tell me which side you think is favored. tired of drawing dots. All right, so those are the products. Carboxylic acid, again, probably going to be the acid. Water can be an acid or a base. So honestly, you have to think about this a little bit here. Not that you don't have to think about everything, but if we take the H off the O, we get a delocalized anion. If we take an O, if we use electrons on the carboxylate to take an H from water, we get hydroxide. You should draw, if you want, put the H from water on either of those oxygens and see what you get as a structure. This is an exercise I'll leave to you guys, but it should look pretty bad. Like, I want you to get to where you can just sort of see it, but if you need to, when you're studying, work on it on your own. Like, take every H, put it everywhere you can. Always, what's going to happen, the strongest acid in a mixture is going to react with the strongest base. All right? It doesn't really matter how many acidic protons I have in a molecule. Because here, I've got an H on this oxygen, I've got H on these carbons, I've got an H on water. All those protons, in theory, could be acidic. I've got 3 oxygens with electrons that are all different. Any of those oxygens could be a base. There's a lot of combinations there. What will happen is the strongest acid is going to react with the strongest base, always. Okay. So the mechanism again here goes from the O. You might notice now I'm no longer drawing in bonds and electrons there, but they're there, right? There's an OH bonding pair. There's a lone pair on oxygen. Now, what side do you think is favored? Just looking at the structure. Got to vote for right, because we do have a delocalized pair. So anyone think the left is favored? Whole bunch of non-committal folks, all right? So we just went through a hotly contested election where everybody seemed to have an opinion. This is like an off-year city council election. Nobody knows who's running, including 3 of the people who are running. Like, just what's going on? And that's fine here. And this is why this is a much better one to use pKa. So if you follow the lone pair, right, it's localized on oxygen here, and then it's delocalized over here. And so by the same argument that is now covered up by the flying board, that would suggest the right. But there is a penalty to be paid for charges. Okay, so that's always a hard thing. I don't think I can actually keep them all down at this point. If we raise your tuition to $90,000, maybe I can not use paper towels that way. Hi, Dean. What's that? I thought so, yeah. It was a good one, and I said it, and then I'm like, no, that's not, you shouldn't say that. All right. So I did not mean to imply over here. Like, this is something I want you guys to know. Even 10 years from now, you've forgotten all about anything like why. I want you to know that if an amine reacts with a carboxylic acid, the ammonium salt is favored. But that doesn't imply that these charges are like fine, like nobody cares about, the molecules don't care about the charges. So it's true, you've gained a delocalized pair here, but now you've got a positively charged electron-poor oxygen. Right? So we've taken, that looks like exactly the same reaction as the one with the amine. It's just now the basic atom is O instead of N. The atom that's giving away electrons is more electronegative. And that's enough to change this, so the left is actually favored here. And we can look at this by pKa. So the acid on the right, pKa of benzoic acid is about 4.2. pKa of H3O+, H3O+ is H3O+ is the strongest acid you can have in water. Right? If I add a strong acid to water, sulfuric acid, hydrochloric acid, phosphoric acid, if I add a strong acid to water, the water completely deprotonates the acid, and I get H3O+. Okay, so 4.2 is greater than 0. The equilibrium constant here is going to be 10. Well, actually, so equilibrium is always saying the right is the products. So this would be 0 minus 4.2. I can do that math. So by about a factor of 10,000, the left is favored. Okay? And what that means, but again, like 10,000, in our daily life, 10,000 to 1 is a huge ratio. Right? If I have $10,000 more than you, if I have 10,000 times more dollars than you, hopefully that's not $10,000 to 1. But if I have $10,000 time, you get the idea. I have a lot of money. Okay, so, but in reality, like you and I probably don't share 10 to the 20th dollars. If we did, we wouldn't care about a factor of 10,000, right? So if I have 10 to the 20th, if I start with 10 to the 20th, 10,000 here, 1 over here, but that 1 is like a tremendous amount of molecules, right? So in reality, in solution, that's why we would say a carboxylic acid is not a strong acid or base. Or sorry, it's not a strong acid, it's a weak acid. What you've probably heard up to now is that it partially dissociates. Right? Something I want to emphasize, I don't care if you use the term, acids don't dissociate. All right? H's don't leap off of atoms. A base has to pull the H off. Again, chemical reactions are driven by electrons. And if we come back over to the Lewis theory, the base is the electron donor. So the electrons drive the reaction. The base drives the reaction. The other thing we can draw here is a reaction energy diagram. This is going to look a lot like what we did for conformations. A reaction coordinate is kind of arbitrary. In this case, it would be easy to pick out. We would either make it like this OH bond distance or the new OH bond distance, and we would plot the energy versus that distance. And what you'd find is, so the left is favored, start is favored, it would look something like that. All right? So starting material on the left is favored, product on the right. We just arbitrarily say the product is whatever's on the right and the starting material is whatever is on the left. Starting material is the same thing as reactants. Reactants is a left to right thing. Reaction in products is a left to right thing. In reality, it doesn't matter how I come at this. Like if I mix, I could have sodium benzoate and H3O plus and chloride, and I mix those together, and equilibrium will wind up in the same place. So some stuff to put in here. For this is a single step reaction. There are no intermediates. We'll see some reactions coming up where we have some intermediates. That would be a little local minima. All right, so transition state is just the high energy point between the two steps. If it's a single step reaction, it's the high energy point between the reactant and the product. The difference in energy between product and starting material is the delta G of reaction, the change in free energy in the reaction. For every spontaneous reaction, this is downhill. Right? Delta G for the favored stuff is lower than the delta G for the unfavored stuff. And actually, when I write energy over here, what I really mean is G, Gibbs free energy. Again, Gibbs free energy, I had a colleague who retired a couple of years who would ask me, how how we cover chemical reactions in like Orgo 1. How can we talk about chemical reactions if we can't talk about Gibbs free energy? And I said, well, we talk about Gibbs free energy. So he was a pea chemist. He was a really brilliant pea chemist, I guess. He's retired, he's not dead. And for him, Gibbs free energy is like 3 textbooks, right? It's like you can just dive deep into this. For me, I'm going to write this equation. These equations, I guess. Maybe you've seen this. For a chemical reaction or for any process, the change in free energy is equal to the change in enthalpy minus the temperature times the change in entropy. And again, enthalpy and entropy are hugely complicated things. You can roughly approximate them. Change in the delta H, change in enthalpy is basically bonds breaking and forming, right? If I make stronger bonds, delta H goes down. If I make weak bonds, right, if I break a weak bond and I make a strong bond, delta H goes down. If I break a strong bond and make a weak bond, it goes up. Entropy, we all think we know what it means. Unless you've done a lot of math, you don't. Entropy is roughly disorder. Okay? The universe is trying to get more disordered. The universe would like to spread us out into a completely uniform sea of subatomic particles. That's what the universe would like. So if you look at this, then delta G also equals the gas constant times the temperature times the natural log of the equilibrium constant. So delta G and the equilibrium constant are related. Bigger delta G, bigger equilibrium constant. If delta G is 0, that means the two sides are exactly equally favored. The equilibrium constant is 1. Both sides are equally favored. There's the same amount on either side. So we have, I apologize to folks at home, this may be hard to read. Turn up the contrast or something. This gap here, so product or starting, but the gap between the product and the reactants, that's thermodynamics. Okay? And we can't really change that. Humans don't have the power to change the difference in stability between these mixtures. We can measure it. We can find circumstances where it favors what we want to have happen, but we can't really change it. At a given temperature and pressure, the delta G between two substances is just whatever it is. Above this, the energy going from one side to the other, this is kinetics. Kinetics is a measure of how fast something happens. How fast do we go from the starting material to the product? It's really, really tempting to say that the bigger the free energy difference, the faster we go from one side to the other. All right? But that's not true. So if it takes, right, if there's a huge difference in energy between the two sides, but there's a giant wall between them, we'll get stuck on one side. All right? I think a lot of analogies work there, mathematical and physical, right? Seawalls work. So you can have, you know, good jazz clubs 10 feet below sea level if you build a good seawall. So that stuff is all in Chapter 6. The curved arrow mechanisms, which is, I'm about to strip that off, right? So this is Chapter 6, the curved arrow mechanisms, kinetics, thermodynamics, a little bit of an intro into Gibbs free energy and whatnot. And then, I can't remember if this is 3 or 6. That's probably a little bit in both. Okay, so a review. In an acid-base reaction, which right now is the only chemical reactions you've seen, sorry.
Going back to that reaction right there, can you just not use ARIO? Is that just like not feasible?
Yeah, it really doesn't work out. All right, and I mean, this is, I put this general guide in, but I didn't emphasize that enough. And this is something that I think students are, I complained a lot as a student, you guys probably do. Like, this is really a legitimate complaint. ARIO is really a rough guide. There are going to be a lot of circumstances where it's wrong. All right, we're going to talk about some. There'll be some that I sort of think. I actually think induction and orbital are no big deal. Like I would like you to look at them, but they're not going to be a lot of points on the exam if they're even on the exam. A and R are important. But like I said, they just aren't always. Like here, the oxygen with the electrons is the same. You've got resonance over here on that one. I guess induction maybe, but orbital winds up the same. The point is, it really is the charge. All right, and this is something else about electronegativity that doesn't seem to, I have trouble with it. We're taught that electronegativity just goes by element, right? A carbon has this electronegativity, an oxygen has this one, a chlorine has this one. But the electron affinity for an atom, a particular atom, depends on what else it's bonded to. All right, so the electronegativity of this oxygen is not the same as the electronegativity of that oxygen. Right? One's an O minus, one's a neutral O. The O plus has got a different electronegativity. So charge is important. I mean, it is confusing. And like I said, I'm glad you guys on the amine plus the carboxylic acid recognized that the delocalization was important. But really what makes that work is the positive charge winds up on a not as electronegative atom. Okay, so if you wind up with that positive charge on an oxygen, and this is an empirical thing you have to learn. It just doesn't, it changes which side's favored. And again, like I can't emphasize this enough, we go from an equilibrium constant of like 10,000 to an equilibrium constant of 1,000,000. That's a 10-fold order of magnitude difference. So that's a pretty big difference. Coming back, doing that again, right, if you look over here, did I put them in? Yeah. Like this first reaction I did, hydroxide and HCl, pKa minus 7 to a pKa of, say, 15. That's now an equilibrium constant of 10 to the 22. So if I have a tenth of a mole, I have 1 on the right, sorry, 1 on the left. That's essentially completely irreversible, right? Somewhere around an equilibrium constant of about 10 to the 12th, 10 to the 13th, we just say it's an irreversible reaction. I'm a minute shy. I'll take some questions, but anybody have any? Yep.
While we're talking about ARIO, so is it mainly used to distinguish between like stronger, weaker bases, or is it?
Yeah, that's a great question. ARIO is almost always used to look at the lone pair or the base, right? So it's hard to compare the acids because the acids usually have an OH bond. And you can sort of, if you look, so for example, right, this OH bond here, the carbonyl is pulling electron density away from this oxygen. Means that oxygen is going to pull electron density out of that OH. So the OH bond's more polarized. But it's not as polar as this one, right? So now you've got an oxygen with a positive charge. That oxygen is super electronegative. That positive oxygen desperately wants more electrons. So you can use it for the acid, but it's way more common and usually easier to apply it to the base. What I want to emphasize, again, pick one, all right? Don't compare the acid and the base. Don't compare the base and the conjugate acid. Compare the acid with the conjugate acid. And that way you're comparing, right? I'm comparing the thing with the Cl in it and the thing with the OH in it. Or you could compare the hydroxide and the chloride. Which of those is more stable? And if you're given a pKa, or I'm going to give you guys sort of a pKa table I expect you to know, and again, in regions. Nobody should ever memorize like the pKa of this molecule is X unless you're working with that molecule frequently. But you should kind of know regions, and I'll send that to you. If you have the pKa's, use the pKa's. All right, because ARIO is always kind of a judgment call. All right, yeah.
So like I looked at the pKa table. The best way to go about that one is just by functional group, right?
Yeah.
Just how they're connected.
Yeah. Yeah. Yep.
I just wasn't paying attention for a second. What's the equation underneath the Gibbs reactor equation?
That is minus gas constant, temperature, natural logarithm of the equilibrium constant. Yeah. Okay, so I said this in my announcement, but I don't think everybody reads all my Canvas announcements. Last week in NMR, sort of both Tuesday and Thursday were pretty much the same. Like if you came to Tuesday, you didn't necessarily need to watch the video for Thursday. It won't hurt you, it's different problems, but you could just work the sheet. This week, Thursday's class is gonna build on this. You guys at home, I really hope you're watching this before Thursday. So watch Thursday's class. And again, I've had this conversation with a lot of people, maybe I haven't been all that clear. You should treat watching that, when I say watching that video, right, it's not Netflix. You're not just like leaning back, half asleep. Sit in front of it, take notes, block everything else out. You don't have to do the whole 75 minutes at once. If you want to do like, there are times when I have kind of a break. If you want to go up to the first break and then go walk around or do something else and come back to it, but treat it like class. All right, I'll see some of you in lab in just a minute. The rest of you, there are office hours posted.